Welcome to this first tutorial on CNN architectures, and in this particular section I will be talking about the LeNet5 architecture and the AlexNet architecture. So let us begin with the LeNet5. We need the libraries TensorFlow, and I need my custom dplot file. I also need the NumPy library. I'll also be needing the specific functions from the TensorFlow for developing the models. So first of all, let us begin with the LeNet5. So it was developed in 1985, and one of the co-authors were Jan LeCun, and it was composed of 5 layers, which is 2 convolutional layers and 3 fully connected layers. So in this particular architecture, one of the considerations they factored in was that the average pooling layer, which is a subsampling layer, had weights at that moment, but later on we see that this is not the case in modern days. So though it had the weights, but nowadays it does not have. So it has been taken, it has been done away with. So it has 60,000 parameters. And if we look at the architecture of the LeNet5, yes, we see that it takes a grayscale image of size 32 by 32, and then there's a convolution operation for a convolution of 6 filters and kernel size 5 by 5 and stride of 1. Activation is tang function. So we see a convolution pooling layer, which does a pooling of size 2 by 2 for stride 2. So we see that actually this, since we have said earlier that the subsampling layers add trainable weights, so we see that the activation for the trainable weights of the output of the weights of the subsampling layers was tang function. But nowadays subsampling layers does not have trainable weights, so they don't have activation functions or any other things to do with training. So we see convolution pooling, and then this is supposed to be a fully connected layer. It's not actually supposed to be a convolution, so it's supposed to be convolution pooling. And then we see a dense layer, that is after flattening from the pooling layer. We see now 3 dense layers, that's one of units 120, 84 and 10, with all of them except the last layer having activation function tang. So it's the last layer having activation function RBF, known as radial basis function. So yes, so this is a representation of the floor of the input to the output of the LeNet5 architecture. So this is how it's implementable. I've used the sequential API to stack the layers one on top of another. So because there's the activation RBF for dense layers is not really available pre-built in the TensorFlow framework, so I defined a custom dense RBF layer, which is here. So this is how I defined it. Of course, I got help from the Stack Overflow. So this is how the dense layer with activation radial basis function actually is. So you can read more about it, but this is how it's implementable. Then I call it in the last part of my model, since it's the last layer. So actually the LeNet5 did not use the ReLU activation function, which is the most popular activation function for intermediary layers in CNN architectures, with the last layer usually being either the softmax or sigmoid, mostly in most cases. So then therefore we can now see the LeNet5 architecture. So we see like almost 60,000 model parameters. Yeah, and this is how the flow of of input to output with the number of parameters for each layer. And we can test a function where I create a dummy image with the composed in a single batch. So this is a dummy, then we see the shape. Yeah, so the LeNet5 did not use the ReLU, but it was one of the pioneers of CNN architectures, and it was used for recognizing unwritten digits and this is one of the pioneering architectures which led to the start of CNN architectures for deep learning. So the next I want to talk about is the AlexNet, which was composed of 8 layers, and it was built on top of the LeNet5. So it won the 2012 ImageNet large scale visual recognition challenge by a large margin, at achieving a top error rate of 17%. So by the time the term top 5 error rate essentially means that of the 1,000 probabilistic outputs of the AlexNet, the top 5 probabilistic outputs were essentially, so top 5 error rate means the top 5 probabilistic outputs from the 1,000 probabilities were not part of the, essentially the correct prediction was not part of the top 5 probabilities in our 1,000 probabilistic outputs of the AlexNet. So that means 17%, that means 83% was correct in terms of top 5 predictions of our AlexNet architecture. So it really was a successful architecture, since the second architecture after the AlexNet had a top 5 error rate of 26%. So that's a really large margin, and hence it really catapulted the need for research in this convolutional neural networks. So it was developed by Alex, and it is similar to LeNet5, only much larger and deeper. So it's also introduced the first the activation function known as ReLU, and also introduced the dropout regularization, so the dropout regularization, what it does essentially, if the weights are near 0, and also for those neural connections that really don't contribute to the output predictions of a certain label, they are essentially neutralized to 0. So it regularizes these layers to minimize computing resources, and also to reduce overfitting. So when we see the architecture of AlexNet, so we see that it took an RGB image of size 227 by 227, and it acted on it with the convolution layers and the max pooling layers, and then afterwards it was flattened to, then taken to the dense layers, where the last layer was add an output of 1,000 with activation softmax. So it's also one of the layers where there were consecutive convolutional layers following one another. Since initially it was thought that convolution layers, after convolution layers there's max pooling, but in this kind of architecture this is where there was consecutive convolution layers following one another. So the implementation essentially is this is the implementation. I've used the functional API in this implementation. Yeah, so after developing the graph of layers, I now create the model from the graph of layers, and then we can view the summary for the AlexNet. Yeah, so this is a brief of the AlexNet architecture. So as we had said earlier, the dropout was introduced. So the dropout can be added into the outputs of layers F9 and F10. Then also the images fed into the AlexNet architecture were randomly augmented by random shifting the images by various offsets, such as horizontal flipping and changing the light conditions such as hue, contrast, brightness, and so on. So we can see that one of the factors which led to AlexNet being really good at the predictions in the ImageNet large scale visual recognition challenge was dropout. So essentially, dropout was added to the layers. So in this case, to add dropout layer, we essentially say dropout so it's a rate of 50%, so it should be 0.5, then F9, then also dropout, and also the output of F10 is passed through another dropout. So essentially we've introduced dropout now to the linear layers of F9 and F10. Yeah, so this is how we can introduce dropout. And also random augmentation can be done using the augmentations library, which can be changed the TensorFlow input for preprocessing. But also there is a generator for data augmentations within the TensorFlow library. So layers, I did not import the dropout prior, so I'll just have to do this. Yeah, yeah, so we see the dropout for the outputs F9 and F10. Yeah, so that's all on the LeNet5 architecture and the AlexNet architecture. So thank you for watching. In the next video I'll be talking about the next architecture, which is the VGG architecture.